our first scientific speaker of the day, Martha Constantino, and she will tell us about the inverse problem in hadron structure. And we're very much looking forward to your presentation, Martha. Please go ahead.
Thank you, Alexander. I guess you can you can see my slides and you can see the cursor. Is that correct?
Yes, we can.
All right. Good afternoon to the Europeans and good morning to the Americans. It is great to have these meetings. It feels like I'm talking to a group of people that are interested in the same issues, and I'm very happy to begin the scientific part of the conference with a discussion on the problem at hand for hadron structure calculations. So the way that the inverse problem manifests in hadron structure calculations is related to the reconstruction of some very important quantities, the X-dependent PDFs. I will introduce this very briefly for those who are from different fields. I will discuss where the limitations of the lattice data enter and cause these issues that we have to address. I will also discuss different ways to analyze data unrelated to the inverse problem, but the point I want to make is how different analysis methods can affect the severity of the inverse problem. And I also want to touch on naive versus advanced reconstruction methods that we use in our calculations. All right, so as I said, the problem we have is related to the inverse problem is the PDF reconstruction. And these PDFs are very important quantities to understand hadron structure, both theoretically and experimentally. They have been under investigation for more than half a century already now. And we know that access on the hadrons can be extracted from high energy scattering processes. We are very excited that EIC will also give an opportunity for a wealth of new information coming on this respect. But even looking at simple processes like deep inelastic scattering, we know that because of asymptotic freedom and the energy scale of such experiments, the cross-section of the process can be decomposed into a perturbative part, which contains all the information of the process. But more importantly for us is that it contains a contribution, which is the so-called non-perturbative part that is related to the structure of the hadron. So this is the quantities that we are after. And you can extract them either from experiments or from theory. But in the end of the day, you get this kind of functions that are to leading order in the energy scale. They are probabilistic functions, and they give information on the different partons, such as the up, down, quark, anti-quark, the gluons, and how these behave within a hadron and with respect to the momentum carried. So this is the functions we want to extract. They are the simplest functions are one-dimensional. They depend on the x, which x is the momentum fraction carried by the partons. And we want to reconstruct this x dependence from the lattice. So experimentally, it is a different discussion, but theoretically, we do not have access on the x directly. I will explain this soon. But we want to reconstruct that. So if you look at the definition of these PDFs in the Pardon model, they have physical interpretation when one is in the infinite momentum frame. And in fact, the propagation of the quarks happen on the light cone. And therefore, the relevant matrix elements to discuss the distribution functions require these objects here, which are non-local light cone operators, and I will come back to that. Now, we do our simulations on a Euclidean lattice, and therefore the distribution functions are not accessible directly because of their light cone nature. But recently, it has been discussed that even though we cannot access directly the distribution functions, we can calculate on the lattice some matrix elements of some type of non-local operators. But in this case, your non-locality appears in the spatial direction. So this is the Cori gradient that we calculate on the lattice. This is the most computationally challenging component. I am not going to discuss at all this part. For the sake of this talk, we assume that we know how to do the simulations. We address signal to noise ratios and improvement methods. So assuming we have this. This is the quantity we want to extract. This is the quasi-distribution. So it's not the usual distribution, it's the quasi-distribution. And again, for the sake of this talk, I am going to assume that the extracting the distribution function from the quasi-distribution, it's a well-known approach. It's not related to the inverse problem. It has its own challenges, but I'm not going to discuss that. So the inverse problem manifests when I am using the raw lattice data to get these quasi-distributions, and these are linked through a Fourier transform because the matrix elements are defined in coordinate space, and the natural variable is the length of the Wilson line that enters this non-local operator, which the fields are separated by some distance z. So this is the variable on the matrix elements, but one has to take a Fourier transform to go to the X space where the distributions are defined. So what I want to focus on is how to perform this Fourier transform in a way which it's not naive, because naively we have an inverse problem. It would be an omission to not to mention that there are other approaches than the one equation I just summarized to get the X dependence. I am not going to talk about this with the exception of two methods. There will be a talk by Kostas on Wednesday and Kefe on Friday on different approaches and how the inverse problem is dealt with. So the limitation of lattice data with respect to the reconstruction of the X dependence is related to this integral. And how do we see this issue, and what is the severity of the issue can be summarized on this slide. As I said, these matrix elements are defined in coordinate space. What we calculate on the lattice are matrix elements of operators where the fields, in this case, the quark fields, are separated by distance 0, 1 lattice space, 2 lattice space, 3 lattice space. So the value of z keeps increasing as much as possible, which is half of the lattice extent in the spatial direction. And the kind of data we get, it looks something like this. This is the matrix element as a function of the length of the Wilson line. As you increase this, it means that your fields are separated further apart. And the further you go, then this matrix element decays. One important aspect of the calculation is the fact that these matrix elements need to have boosted hadrons, and this is very important because this allows us to understand this methodology as a Lorentz Fourier, as a Lorentz transformation to go to the light cone. So this is an important parameter, and basically the quasi-distributional approach requires that the momentum boost should be as much as possible. So you keep producing data with different values of P, and you keep going until systematic effects permit you, and also the signal. So here we were able to do it for 1.4 GeV. And these are the blue points. Also, these matrix elements has a real part and an imaginary part because of the presence of the Wilson line. So as one can see, we are no longer able to do this Fourier transform in the continuum way, because for one, we have discretized values of Z. These are multiples of the length of the lattice spacing. And in addition to that, we work on a finite lattice, so we cannot infinitely increase Z. And unavoidably, this means that your integral becomes a sum, and you also have a truncation of the Fourier transform up to some values of Z. And that's exactly the aspect which is ill-conditioned, because one has to regularize this integral, and the way that this is done is by imposing some assumptions that introduce bias in the calculations. In addition to the challenges of the finite lattice data and also the discretized nature of the lattice data, is the fact that these operators need to be renormalized. And the renormalization is not trivial as for local operators. It's not only logarithmic, but it contains a power law divergence. And therefore, this it's a contribution of Z over A. So as you can see here, these are just the Z factors. As you increase the length of the Wilson line, these Z factors blow up. And that's how the evidence of the power law divergence appears in the data. And what is the consequence of this, and how does it affect the lattice data and the inverse problem? Well, if you look at this plot here, you see the data I showed you earlier, which are the field points for the real and the imaginary part. You have some nice feature here where these seem to decay at 0 as you increase the length of the Wilson line, which means that your matrix element don't seem to contribute from this point onward. And similarly for the imaginary part. But the bare matrix elements are not cannot be used unless they are renormalized, and this is shown with these open points, which is basically the matrix elements I showed in the previous slide multiplied by the Z factors in a complex way. And the consequence of this, because this is increasing very fast, you have this bare matrix element to be slightly non-zero, but suddenly they become, they shift away from 0, and therefore this spoils the nice feature of the raw lattice data. And why is this problematic? It's problematic because we have to truncate the Fourier transform, and it's not trivial where can you truncate. One way to think about it is to say, I am going to truncate where I see the matrix element to go to 0, and therefore whatever I neglect does not contribute. But this is only true for the bare matrix elements. If you look at the renormalized, it's not clear where to cut. If you take this line here, for example, where you see the real part going to 0, the imaginary part is highly non-zero. And as you move this away to higher Z, then the imaginary part approaches 0, and this moves away from 0. So there is this issue that is related to unphysical oscillations, as I will show next. But the message here is that having a naive Fourier transform by just cutting some Zmax, it's really problematic. It relies on assumptions about the magnitude of the matrix element and deciding where I want to cut this. And as one can imagine, there is no unique solution to the inverse problem. Trying different values of where to truncate, it gives these functions for the naive Fourier transform. The periodicity of the Fourier transform leads to this oscillatory behavior. And this propagates into the physical matrix elements. These are the distribution functions after you do the so-called matching procedure to go from this to that plot. So this is basically what we want to compare with phenomenological fits. And as you can see, there are still these physical oscillations propagate here. We know that the distribution functions should not have this oscillatory behavior. And depending where you truncate, you have these enhanced or not. And it's not clear what is a good choice. And also it's not clear if increasing Z max, the issue becomes better, because as I showed previously here, by increasing Z max, this becomes more negative while this approaches zero. So the message here is that we really need to seek for other ways to reconstruct the PDFs. We used to have Fourier transform, the naive Fourier transform until a few years ago, but now the field is moving into improving these quantities. And alternative approaches, one of the things that was suggested was Backus-Gilbert, that was mentioned also in the break. It was, of course, the method is very old, but the group of Costas has rediscussed this in the context of PDFs. And this is a model-independent criterion to reconstruct. It relies on minimization of the variance of the reconstructed function with respect to the statistical variations of the input lattice data. Also, the reconstruction is applied on each value of x, and it starts by separating the exponential of the Fourier transform into its sine and cosine components. So basically, the reconstructed quasi-distribution is contained. It's comes from this function here, where the vectors a or alpha are d-dimensional vectors, and d is the number of input data. And as Alexander mentioned previously, the solution, at least for Backus-Gilbert, directly depends on the number of the input data. So it's a d by d space. So in summary, this approach relies on defining these d-dimensional vectors alpha, which are the approximate inverse of the kernel function k, where k is the cos or the sine parts of the exponent appearing in the Fourier transform. And the optimization conditions based on the Backus-Gilbert, which I'm going to show next, lead to this relation for the alpha, where, as I said, these are the approximate inverse of k. So delta is the approximate Dirac delta function with minimized width. And as one can imagine, the quality of the approximation depends on d, meaning the number of the input data. And one can work out the minimization, which leads to this relation for alpha that depends on the D by D matrix and also this U vector. I'm not going to focus on the applicability of the Backus-Gilbert. I want to only show how this affects the lattice data. I'm going to only mention this raw parameter, which regularizes the matrix element to make it invertible. One has to test different raw values. Empirically, we find that raw equal to the 10 minus 3, it's a good choice. If you try to go lower, then you have contributions from small eigenvalues of the matrix M that makes this reconstructed PDF to have large oscillations. And there are other variants of the Backus-Gilbert, such with preconditioning or not. So I'm running a bit out of time, so let me focus on the results. This is now the reconstructed with Backus-Gilbert. As we increase Z, we see that the unphysical oscillations here decrease. Let me compare this with the naive Fourier transform. We see a huge difference, which with the Backus-Gilbert moving in the right direction. And another question is on the how the addition of the lattice data, meaning increasing the dimension space D, affects the Fourier transform and the Backus-Gilbert reconstruction. So here is now, these are not the quasi distributions, these are the final distributions after you apply all the necessary steps. And we see that the Backus-Gilbert leads to this nice behavior. You no longer see these oscillations, and this approaches the physical expectation for these quantities. So the improvement is already seen here, and we also see a less dependence on the Zmax as compared to the standard Fourier transform. And this is just a comparison between at Z equals 10, the naive Fourier transform and the Backus-Gilbert, how they appear. And in fact, you see that the Backus-Gilbert approaches the expected function, which are shown with gray. And if one wants to improve the number of data, one needs larger volume, so you have more Z, but also to control systematic uncertainties, you need finer lattice spacing. Alternative analysis method is the pseudo distribution functions developed by Anatoly Radiushkin. This uses the same lattice data as we did for the quasi PDFs. One of the practical differences is that here one works with the Joffre time, which is the product of Z times the momentum boost, and therefore all the lattice data at all different boosts are used, and suddenly you increase the set of data you have available. And if you were to analyze this data with respect to the quasi PDFs, you analyze these momenta separately. And what I showed you previously correspond to the highest momentum, which are the blue points here. So now we have many more data to include in our analysis. Also, the method relies on taking ratios of matrix elements that cancels the divergences, and you don't have to renormalize the way you do for quasi-PDF. Despite the improvements and the advantage here, the inverse problem is still present when one tries to take these Q quantities, which are the Joffre time distributions, and convert them into the PDFs. There is also a Fourier transform there. So the Backus-Gilbert, the naive Fourier transform are applicable for these quantities. But alternative reconstruction techniques is the fitting ansatz, where one can fit the function into a form, and again, it minimizes the chi-square function. Let me move on to show some results. So this is a comparison of the reconstruction methods. If you focus on the standard Fourier transform, you see that by chopping the data at a small value of z, you have these unphysical lines. By increasing z, you see that the standard Fourier transform moves towards the phenomenological, but still it has its oscillations. If you now focus on the green points, which are the Backus-Gilbert, as you increase z, you see that again it approaches the expected values, but the oscillations decrease. And also, if you look at the magenta data, these are the reconstructions using a fitting ansatz. This already is at small values of the truncation of z. It approaches very well the expected form. And one thing I should mention is that the errors of the fitting reconstruction are more honest, because they reflect the lack of data. If you look at the data for the naive Fourier transform, they seem too accurate for Z max, but this is not correct. This is a comparison. Again, the fitting reconstruction is the best function for this data, followed by the Backus-Gilbert. And my message through this analysis is that this is really necessary if we want to claim we understand a hadron structure, or we move towards understanding the hadron structure. And by including all the systematics related to the inverse problem is important to do before comparing with phenomenological fits. Also, this is not related only to comparison, but how can we help in the constraints of PDFs? We know that for some functions, such as the unpolarized, these are well known experimentally because we have a lot of experimental data, but other quantities, they lack data and therefore are not accurate. So the question is, can we help? And the answer is yes, only for the cases where we don't have enough data. You see here the helicity PDF, a different type, where the red data extracted from experiment are improved once the lattice data I showed previously are included in the analysis. So this is what we want to strive for. There are different approaches to do that, and we want to do this for more quantities. And in summary, I want to emphasize that we have to move past naive reconstruction techniques, such as the standard Fourier transform, the derivative methods. And we are now in the era where advanced reconstruction methods are in need. I have talked about the Backus-Gilbert and the fitting reconstruction. Kostas will talk about other methods such as Bayesian methods. And we are not there yet. We still have systematic effects, but things are certainly moving in the right direction. Thank you for your time, and apologize for taking more time than I should.
That's fine. Thank you very much, Martha, for this very nice overview of the community efforts on hadron structure and the inverse problem. I think since we would like to encourage discussions, I think it's okay if we open the floor for a few questions. Yes, Harvey.
Hello, here's Harvey. Thanks for your nice talk. I have the question: if you understand the connection, increasing the number of data points by increasing the volume, what benefit would that bring? And instead, decreasing the lattice spacing, what benefit would that give you?
Yes, this now is not behaving, so I cannot go back to my slide, but I can tell you verbally that if you remember the initial lattice data are defined in coordinate space, and there are limitations how the non-locality of your operator, how much can you extend it. So if you have a volume of 32 cubed, you can have the length of the Wilson line being from -16 up to +16. But if you have a volume of 80 cubed, so in the spatial direction you have up to 80, it means you can have keep increasing the non-locality of the operator up to, let's say, 40. So when you do the reconstruction, you have, instead of having 15 data entering the reconstruction, you're going to have 30, for example. So that's one way to help the inverse problem. Now, the lattice spacing, I didn't say this very clearly because it has to do with the reconstruction of the PDFs. You have to stay in a region where it is considered a perturbative region for Z. So if you have a lattice spacing which is of the order of 0.1 Fermi, it means already at Z equals 8, you are at 0.0, you're at 0.8 Fermi.
Yes.
And that's very large. So if you look at the pseudo PDF approach, you cannot go beyond that because the matching formalism which is required, you have to stay in the perturbative regime. If your lattice spacing is, let's say, 0.06 Fermi, then immediately, if you want to stay at 0.8 Fermi, you can have more lattice data entering in that region. So that's two ways to help in the reconstruction of the in the PDFs, no matter what approach you're going to use.
Any further questions? If I may, I think there was a very interesting point that you brought up, Martha, that the Fourier transform by itself holds somehow challenges for us, because it's sometimes presented as if we once develop real-time algorithms for gauge theories, then access to the spectral function or other quantities just depends on the Fourier transform. But this is then again a matter of competing timescales. How long do you have to resolve? So what's the resolution? What's the length of the signal that you have to do the Fourier transform? And for example, one of the things that our group has been working on is classical statistical simulations, where we do have real-time data and then need to do the Fourier transform. And exactly the treatment of this oscillatory behavior, if your signal has not died down, is something that we also in the real-time domain have to deal with. And one of the ideas there is to use these so-called windowing functions. And that might be interesting to look at how these tie in with the Backus-Gilbert approach of resolution, because they allow you to somehow smoothly damp down your input signal for the Fourier transform so that it actually goes artificially to 0. And that translates then to a reduction of the oscillations in the Fourier transformed result. And that might be related somehow to this idea of again, overall resolution in the Backus-Gilbert.
Okay, that's very useful. I will definitely think about this and how it can be applied on the PDFs.
That would be interesting. John, maybe as a last question.
Thanks, Martha, for the clear talk. It was very clear for a non-expert like myself. Just a question, why, if this is a coordinate space quantity that you're computing, why are you restricted to on-axis separations? Why can you not look at off-axis separations as well?
Oh, okay, yes. So this, because eventually what you want to do is you want to reconstruct, you want to match the lattice data with the actual distribution functions. The distribution functions are defined on the light cone, and therefore you need the momentum boost of the operator to be in the direction of the Wilson line. So that's because basically, if you want to match it, if you want to match the quasi-PDFs with the actual PDFs, you need to make sure the infrared physics is the same, and any differences between the objects are in the UV regime, and that you can calculate perturbatively. So we have restrictions on where you want this, what can you do with these matrix elements. And basically you have to do the extension, the non-locality to be in the same direction as the boost.
So you would have to have an off-diagonal boost as well if you were, or do I not understand? I mean, if I had I can make the momentum in the same direction as the separation in an off-diagonal situation as well.
The direction of the boost of the matrix element has to be in the P plus direction. So you don't have flexibility to do this in perpendicular than the light cone. It has to be basically in the P3 direction that I showed here, because we take the light cone to be, we take P plus to be P0 and P3. So this is a constraint of the matrix elements by construction. If these lattice matrix elements are to represent physical quantities that are defined naturally on the light cone, because this matching is assumed as a Lorentz transform. So you take these matrix elements, and by matching it, it's kind of rotates on the light cone, and this can be done only if the direction of the boost is in the P plus direction.
Thank you. Javi, is this a direct question as a follow-up, or would you mind if we postpone your question to the discussion session afterward?
Maybe I can just say what I was thinking about. So it's
Sure.
the question of whether it's easier to determine the PDF at small x or large x. I would have expected large x, but that's where you also saw these oscillations, and so that was my question.
Yeah, so you're right. The small x region is it's out of reach because for many reasons. First, the lattice data are not reliable in that region. Second, there are higher twist contamination in the region. So we cannot compete with experimentalists when they talk about the small x region. For us, the closest we can get to x equals 0 is about 0.1, 0.15 for the x. And you're right, the oscillations manifest mostly, and they show up in the large x region. And ironically, this is the region which is not too interesting, because you know that these distribution functions, they decay to 0. But also the higher twist effects also are enhanced in the large x region. But unless you understand these issues for a region where you know how the PDF should behave, how can you trust the intermediate x region? So this is our strength. Our strength is somewhere between, let's say, 0.2, x 0.2 and 0.78.
Okay, thank you very much.
Thank you very much. And let's thank Martha once more for this very nice presentation. And we continue to our second speaker of the day, Julian Orban, who is going to tell us about reconstructing of QCD spectral functions with Gaussian processes.
Yeah, can you hear me all right and see my slides?
Yes, are they already on full screen?
Yeah,
Yes.
actually,
Okay.
yes. I don't know why the bar up
Okay.
there is visible, but
Then we will try to do it in this way. Very good.
okay.
Please go ahead.
Okay, yeah. So thank you, Alexander, for this very kind introduction, and also thanks to the organizers for the opportunity to give a talk at this interesting workshop. I'm currently a PhD student in the group of Jan Pawlowski in Heidelberg. So correction to the information on the website, I don't carry the title of doctor just yet, but probably next year. And I'm going to talk about reconstructing QCD spectral functions with Gaussian processes. Which is also the title of this paper that appeared recently. Can you see my cursor, by the way?
Yes.
Okay, good. And yeah, and so that was work done in collaboration with these lovely collaborators down here. And I've already given a version of this talk at the Lattice conference. So if you've already seen it, I apologize for the potential boredom I'm instilling in you, but I do have a little more content due to the more lenient time constraints. So before I even get into it, I want to quickly flash this teaser slide to catch your attention. So what you can see here are the ghost dressing functions and gluon propagators from lattice QCD simulations at the physical point and from functional computations. And the red curves are the correlators that we obtain from the spectral functions that we computed in this work. And as you can see, they do agree with the lattice data within statistical uncertainties, although it seems to clearly work better for the ghost than for the gluon. And I will comment on this later, of course. But now that I've shown the clickbait, if you actually want to know how the spectral functions look like, you will need to stay to the end. So I don't think I have to actually motivate a lot why we are interested in QCD spectral functions, at least at this workshop, but just nevertheless for completeness. So as you know, imaginary time is well accessible by now via non-perturbative approaches formulated in Euclidean spacetime, so lattice simulations, functional methods. But accessing Minkowski correlators of the theory still remains a notoriously difficult problem, unfortunately. Or maybe fortunately, because it means I might actually be able to find a job in this field after my PhD. So please refrain from solving the problem until I have graduated. But quantitatively, understanding real-time dynamics of QCD would, of course, have a number of interesting and important applications listed here. And I'm sure there are many more that I'm unaware of. And of course, one of the most prominent approaches to access real-time is via spectral reconstruction. So just to repeat some basics, so I assume that the two-point correlation functions admit a Kellen-Lehmann spectral representation defined here as a convolution of the Kellen-Lehmann kernel, which I call K, and the spectral function rho. And this is, of course, the central object of interest here. And it's basically related to the propagator by evaluating it on the imaginary axis. And so for asymptotic states, the spectral function is just the probability density for excitations to be created from the vacuum in the presence of the corresponding quantum field, in which case the spectral function is positive semi-definite. For propagators of quote unquote unphysical fields, such as gauge fields, the spectral representation may still hold. However, non-negativity may be violated. And in that case, the existence of a spectral representation reduces to a statement about the complex structure of the propagator. And for this talk, I will simply assume that a spectral representation does indeed exist. Now, some important properties of the ghost and gluon spectral functions that we computed in this work, denoted respectively by rho C and rho A. First, one can show that the spectral weight vanishes. In the case of the gluon, this is just the well-known Ullmann-Zimmermann superconvergence condition. And also, spectral functions generally decompose into resonance peaks and a continuous part. And for the gluon, we actually only have the latter. The ghost spectral function exhibits an additional particle peak at vanishing frequency due to the infrared 1/p² behavior of the Euclidean ghost propagator. Now, one can think about obtaining rho from G via analytic continuation, but as far as I know, that's very problematic if G is only available in terms of a discrete set of data points at specific momenta, which is the usual situation. And then normally the strategy is to invert the integral transformation, which is a a well-defined linear inverse problem in principle, but as Anthony said, it is ill-posed, or you might also say it's heavily ill-conditioned and needs to be regularized. And of course, as you know, that has inspired a lot of work in this direction in the past. And when I started my PhD, I was purely interested in the numerical and statistical aspects of this problem. And I had very naive assumptions about how hard it actually is, you know, being young and innocent. And that just meant that the inevitable existential crisis when I discovered the true difficulty was that much harder, and I'm still recovering from the shock. But I still think the results we obtained in this project are very promising and give lots of support to this new method we investigated. It's not actually new, but it's, I guess, kind of new to this field. And I'm also not an expert in any of the other prominent methods at all. And some of you may disagree with this opinion, but or maybe you realize that the method is more closely related to some of the methods that I'm not aware of. So if you notice any parallels, I would be very interested in what they are. But so in this work, we approached this problem using Gaussian process regression. And I will first discuss the basic situation where you have direct observations of the function you wish to model. So that's the usual situation where this method is applied. And then I will go to indirect observations after that. I'm already using suggestive notation here, but for now, this is completely general. So we assume our knowledge of some function rho to be encoded in a GP, which is a stochastic process that represents a distribution over functions over some continuous domain, and it's fully specified by this mean and covariance functions. And that's already one of the key advantages of this method, because we don't actually need to choose a specific functional basis for our desired solution. That often leads to spurious artifacts in the prediction in order to compensate for unrepresentable features. So instead, the GP here represents rather generic types of functions depending on what kind of parameterization one chooses for a C, so what kind of kernel one employs. And so fundamentally, this method operates in the field of functional analysis, whereas, for example, methods using a specified set of basis functions work in the framework of linear algebra, as Alexander has already stated today. Now, if you actually want to evaluate this distribution over functions at a specific set of nodes, omega 1 to omega n, the mean and covariance functions provide you with the appropriate mean vector and covariance matrix that define a finite dimensional multivariate normal distribution. And the mean function is in most cases actually set to 0 because one can show that its contribution can be completely absorbed by the kernel function, and all the design and optimization concentrates on this usually. But in some cases, it can still make sense to choose a custom mean function in order to encode some prior beliefs about the expected solution. Now, based on this prior distribution, we can actually define the joint distribution of some observations rho hat and some predictions at arbitrary points in the domain. And to achieve this, all we need to do is evaluate the covariance between all observations themselves. So that's in the bottom right term. And then between the observations and the predictions, which are on the off-diagonal elements, and of course, between all the predictions themselves. And you just arrange these covariances in this handy 2x2 block form. And the covariance matrix for the observations is additionally equipped with a constant offset on the diagonal, which encodes the magnitude of observational noise. So that can be part of the data set, but if for some reason you have no knowledge of how large the measurement error is, or if you don't trust it, then this can also be estimated from the data within this approach as a consistency check. And now from the joint distribution defined in this way, one can derive the posterior distribution of predictions conditioned on observations in closed form, which is a standard result in probability theory, just for the conditioning of normal distributions. So how does it look like in practice? On the left, you can see samples from a GP prior with 0 mean, some constant overall variance and length scale. And that simply produces, rather generic smooth functions where properties are controlled by the type of kernel and the values of its parameters. So for example, the overall magnitude of the function values and how much it's allowed to wiggle, so to speak, and whether it's periodic or not, etc. And yeah, and so on the right, you can actually see the mean and some samples of the posterior distribution after making observations indicated by these red X's. And the mean prediction and all sample functions exactly pass through the measurements, but there can be considerable variability in between. So this GPR method doesn't only provide a plausible interpolation of your data, but also provides ranges in which other plausible solutions may lie. And this particular instance here shows the result when you assume that your observations are perfect. So in this case, sigma n is set to 0. And if you actually are in a realistic setting, there will of course be some observational noise or measurement error on your data. And in that case, it would look more like this. Now these two plots and also a few more later in the presentation are taken from this wonderful blog post, which in my opinion is the single best introduction to GPR that you can find. And it also includes a lot of simple code examples where the framework is built completely from scratch using NumPy, in contrast to many other tutorials where just some library is used and the interesting details are hidden behind several levels of abstraction. So if you want to get started with this topic and method, I really highly recommend checking this out. Okay. Now that I've discussed GPR with direct observations, the question is of course how one can do spectral reconstruction with this method where the observations are indirect. So let's start at the same place. We assume our knowledge of the spectral function to be encoded in a GP, but this time around we just don't have any observations of this function directly. But assuming that we already have this expression, one can derive a finite dimensional multivariate normal distribution for observations of the correlator. So for a discrete set of observations, you just need to apply the forward process, which in our case is the Kellen-Lehmann integral. And because that's linear, it preserves the Gaussian statistics. And so you get a finite dimensional normal distribution for your correlation function values. And the cool thing about this is that due to the inherent analytic tractability associated with Gaussian statistics, we can actually do inference also in the opposite direction. So what you can do is you can write down the joint distribution of the spectral function and the correlation function, and then derive a closed form expression for the distribution of spectral function values at any frequency conditioned on the set of correlator observations. And so this whole block of math here, that's essentially the same result as I showed before. You just have applications of the forward process to relate the spectral function to the correlation function. So even though we don't have any direct measurements of our desired target, it's still possible to do inference from indirect averages for the object of interest. So that's just a fancy theoretical result. Now, the kernel that we actually used in this work somehow has evolved as the de facto standard for many applications, probably because it has a number of attractive features. So that's the so-called radial basis function kernel, or also called squared exponential. But one could reasonably expect that designing better custom kernels for the problem at hand would be highly beneficial. And I will comment on this again in the end if I have time. But just to note, so we have two parameters in this kernel, two hyperparameters, I should say. So one, sigma c, just controls the overall magnitude. And this L here is a generic length scale. And by modifying this length scale, you can suppress oscillations, and you can tune the method for the resolution that your data allows. So if you want to know further details about this particular method, this framework was formulated in this paper, which is from the field of geophysics or geostatistics, but it's written completely general. And I highly recommend this as well if you're interested in the details. And they actually, I think they also show how the Backus-Gilbert method that was discussed by Marta in the previous talk can be fully understood as kind of a deterministic limit of this framework. So that's really interesting. And I think those guys really know what they're doing, and they have been doing this for, I think, close to 70 years since Dani Kriege from South Africa first developed this method to basically probabilistically predict mineral deposit distributions based on a finite number of measurements from boreholes. And today we can benefit from the work and use this generalized form of the method to, find a different kind of gold, namely real-time QCD. So with all that being said, let's now actually get our hands dirty with some real data. So here you can see the most important facts about the data sets that we used. So we use lattice data from simulations with 2+1 dynamical quark flavors using the Iwasaki and domain wall fermion actions at the physical point. So a pion mass of 139 MeV. Many thanks to the RBC UK QCD collaboration for providing this data, and you can find further information about it in these papers. And further, we use results from functional computations in 2+1 flavor QCD and also Yang-Mills theory, in particular Dyson-Schwinger equations and the functional renormalization group. And also many thanks to the FQCD collaboration, and you can find further information in this stack of papers. Now, the plots you see, they compare the associated dressing functions. So for the ghost, the FRG computation in Yang-Mills was fitted to the lattice data, and it actually fits very well. And we also use another result, which is more recent, from a direct real-time DSE computation in Yang-Mills called the Spectral DSE approach, which was fitted here to the infrared asymptotics. This calculation also provides a direct result for the spectral function, which I will show in a moment. Then for the gluon, we have a similar story. So the 2+1 flavor QCD result that we have here obtained with the DSE approach fits the lattice data pretty well. And I'm also showing here an earlier calculation in Yang-Mills theory, and the discrepancy to QCD is of course more pronounced here. The difference will also show in the associated spectral functions. But I would say that this is expected heuristically because the gluon directly couples to quarks, whereas the ghost only does that indirectly via the ghost-gluon interaction. So you would at least naively expect that differences between Yang-Mills and QCD are more obvious for the gluon. So here again, the results that I baited you with in the beginning. So as I said, they do agree with the lattice data within the given uncertainties, but deviations are generally stronger for the gluon, in particular at the lowest momenta. But also the lattice data here has comparably large errors to the rest of the domain. And I think this will actually likely be resolved once we incorporate this infrared tail from the FQCD data into the reconstruction, which we haven't done for this work here, but I'm very sure that this should improve the behavior here considerably. And so the mean squared errors amount to roughly 5 times 10 to the minus 6 for the ghost and 4 times 10 to the minus 5 for the gluon. And so here, finally, the spectral functions responsible for the correlators of the previous slide, very beautiful. There's not actually too much to say on this slide. I'm just noting already that we have a pronounced quasi-particle peak in the gluon spectral function. So that could give further support to pheno approaches where this is assumed. And also, even though one cannot really see that from this plot, I should mention that we made sure that the Ümit-Zimmermann condition is approximately enforced, at least in the gluon spectral function, by treating it as an additional indirect observation. But in that case, the forward process, so to speak, is not the Kellen-Lehmann integral, but it's just a convolution with the frequency. So that's another very nice aspect of this method, that you can basically include any kind of prior information, any kind of additional condition. You just need to include it as an additional observation and compute the covariances between that observation and everything else. So that can be a very strong programming headache, but conceptually it's very simple. And so this slide is a little more interesting. Here I'm actually comparing the reconstructed QCD spectral functions to results in Yang-Mills theory. So on the left, the ghost is compared to a direct real-time computation using the spectral DSE framework that I mentioned. And what I found remarkable about this result is that the only thing that we fixed in this reconstruction is basically this point here in the infrared. And the remaining structure was obtained completely independently from a completely different method. But as you can see, at least qualitatively, they agree. And since these are different theories after all, you wouldn't expect them to match perfectly anyway. And on the right, I'm comparing the gluon prediction to an earlier reconstruction result from an FRG computation in Yang-Mills theory. And again, the structure and relevant features are qualitatively similar. So first we have a local minimum, then a leading peak followed by another slightly more deep minimum. But the differences between QCD and Young-Mills, as I mentioned, are much more pronounced here. In particular, the Young-Mills result is much narrower. And also this is scaled here by a factor of 100. So there are large differences in the overall magnitude. However, we did find that the positions of the leading peaks are quite similar. And so, yeah, so before I close, I also want to comment on the optimization of the kernel hyperparameters. So as I've mentioned, depending on the values of the parameters of the kernel that you use and what behavior they control, you can get very different results, which you can see in these various instances on the left, which I also took from this great blog post I mentioned. And a specific choice of parameters may just reflect whatever prior beliefs you have about how the solution should look like. But I think one should aim for determining the optimal parameters automatically based on the data at hand. And you can also include prior information in this procedure rather than doing it manually, so to speak. So the most simple and straightforward way to achieve this is by maximizing the likelihood of observations given the parameters, or conventionally, what one does is one minimizes the negative log likelihood of this posterior distribution. So in this optimization procedure, you can include additional prior information by specifying priors on the parameters. And what I plotted here is an example. So this is a fine-grained grid scan of the negative log likelihood for the posterior of the ghost spectral function reconstruction. And there's an additional Gaussian prior on the magnitude parameter, so in the y direction. And that yields a unique minimum, which represents the optimal choice of hyperparameters based on the available data and all prior information. But as I said, it's only the simplest approach to get an optimal solution. You could, for example, also account for some variability in the kernel hyperparameters by integrating over the space with appropriate priors. And so that may improve the reliability of your result because you can actually map out a whole chunk of the posterior distribution and not just some single point. Okay, so that being said, what can we actually do with this, or what do we want to do with this? So these spectral functions are essential building blocks in diagrammatic representations for transport coefficients and bound state equations, such as Bethe, Salpeter, and Fadeev. So it will be interesting to actually put our results in there and see what comes out. But they can also provide first principle QCD inputs for Fino approaches to transport processes, which are based on hydrodynamic simulations. And apart from that, there is a variety of directions to improve the method itself based on our first results reported in this paper. So, you know, what I showed is cool and all, but I think there's a lot of work to be done here to use the full power of this GPR approach. And that includes stuff like smart kernel selection, better optimization methods. Also, there's a lot of work now that connects this to state-of-the-art machine learning techniques. And what's also going to be interesting is to incorporate additional constraints from the theory or from future functional computations, in particular derivative information, because you cannot only define joint distributions of predictions and observations, you can actually also define the joint distribution of the function values and all of its derivatives. So again, that's a major programming headache, but it's not conceptually hard. And so I think including derivative information in the reconstruction will significantly improve the stability and accuracy of the result. And so the immediate next steps in our endeavor to, you know, unveil real-time properties of QCD will be the application of this approach to quark spectral functions. And also in general, we want to do it for correlation functions computed at finite temperature. And so with that, I am done. Actually have 1 minute to go, but yeah, thank you for listening. And I'd be happy to take any questions now or in the session later.
Thank you, Julian, for this very interesting presentation. Do we have questions? Yes, Joniva.
Yeah, I guess I will just start out. So actually, just go back a few slides. So just so I understand exactly, just to couple of slides back, this comparison here. So no, the previous, this one, yes. So the lattice QCD reconstruction, was that your reconstruction, or was that a reconstruction, a previous one?
Oh no, that's the reconstruction in this work. So that's our result.
Yeah.
I
Okay.
should have clarified that. Yes.
Yeah. Now I've forgotten my real question. So actually, so I guess in these sort of just in applications, one of the things that you probably would want to use this for in your framework and sort of the functional framework is the bit-salpeter equation requires the whole propagator in the complex plane. So I assume that's one of the things that you want to be that you can get out of this. So this is a way of doing analytical continuation as well.
Yeah, that's at least the hope that this method would give us enough precision to actually do that, yes. So I think this is the first application of the method to this particular problem. So it's still in its baby phase, I would say. But I am actually convinced that this can be done, yes.
Yeah. Yeah, so you haven't looked at other apps. So I mean, you have enough of your hands with this, so you haven't looked at sort of this applicability to other things that we're talking about in this workshop, I assume.
No, not really. So we have been brainstorming a lot, and my supervisor told me that we picked kind of one of the hardest problems to apply this to. But I would also be happy if anyone would take this and just run with it to any application you desire. So yeah.
Okay, I don't see a question. If I may, so you brought somehow one of the questions that I had in mind. You answered at the end. I was wondering about somehow the smoothness criterion when you showed us the different observations and the Gaussian processes, how they shrink the uncertainty as you add observations. There was a certain range. For example, here, or in one slide back, there was a certain range of allowed uncertainty, so to say, that I guess depends on the choice of these hyperparameters. Yes. So by tuning those, you could make the blue shade grow or even shrink to a certain degree. And now you said that you can relate the amount of uncertainty, so to say, you can estimate that self-consistently from the data. Could you return to this point once more? That you said you were looking at a certain probability distribution where the observations go in, and then it's the probability of the observations given the hyperparameters, I guess. And yes, that you want to maximize.
Yes, so you want to maximize the probability of your observations and predictions as a function basically of the parameters of your kernel. So this is like the simplest approach that you can do, just do a very fine grid scan of this parameter space. But that may also become very expensive if you have more parameters. So this is just a feature of the simple kernel. But yeah, so basically mapping out the posterior distribution as a function of the kernel parameters and then trying to find the optimum is what we did here. But you can do much more sophisticated things. So as I keep emphasizing, that's the simplest thing to do. Yeah.
Okay. Sinead?
Thanks, Alexander. So, Julian, thank you very much for a really interesting talk. I just have a quick question. So you mentioned custom kernels, I think, or smart kernels. Can you say a little bit more about that? I mean, this is in some problem-dependent optimization. Is that what you have in mind, or is it something you've tried?
Yes, so for example, I'm imagining that designing a kernel using a kind of Breit-Wigner-like form could actually lead to these whole computations being done more analytically than numerically. So that was one idea. But also in general, there are kernels where you can control much more of the behavior. So this simple squared exponential kernel we used, it can only basically control the magnitude of your function values and how frequent you allow the function to wiggle in some given domain. And so there is, so you can either design a custom kernel just by having domain knowledge of the problem, but there's also, for example, automatic kernel selections where you define basically a kernel over kernels and then let this decide what the optimum is. So you can automate a lot of that away, which doesn't always make sense probably, but it is certainly possible to try.
Okay, thanks. That's really interesting. Thank you.
If I may, one more question from my side. So one thing that the Bayesian methods have been struggling for quite some time is actually reconstructing non-positive definite spectra. And this is something that is essential, for example, for the gluon spectral function. And I've had my fair share of frustration with reconstructing gluon spectral functions there. And I think there were two things that you mentioned. The first one is that there's no particular choice of basis here, because the choice of basis may lead in the analytic continuation to the occurrence of highly oscillatory solutions. And this is usually what happens, that the Bayesian method, once I allow for non-positivity, just swarms everything with oscillatory behavior. And I'm somehow wondering, is there a good way to see how the Gaussian processes manage to avoid these oscillatory behavior? Is this also, if I look at the top left plot on this figure, I can see that by tuning the hyperparameters, I get somehow a very oscillatory shape for at least the error band. So I can see that I might, by pushing into the very pathologic direction, I might again come back to this oscillatory behavior. But it seems that most of the parameter or hyperparameter choices seem to avoid the presence of these highly oscillatory solutions.
Yes, so in this particular kernel that we use, this is controlled by the length scale parameter. And I guess I could say we're kind of lucky that it has no unstable direction into the smaller values. So if L were much smaller, then the function would also be allowed to oscillate much more frequently. But you can either basically suppress that manually by setting this parameter to some larger value. Or what we also did, at least for the gluon, is we actually modified the kernel such that contributions at very low and very high frequencies are naturally suppressed. And so, but I also think, so if I go back here, I also think it is a question of resolution as well. So what I tested here is I allowed the GP to have much smaller values of the length scale, and then it was also much more narrow and much more peaked, like this Young-Mills result. But then I reintroduced these unwanted oscillations in the low and high frequency domains, and so that's basically it shows you that the data doesn't allow for the resolution of very narrow peaks, and so you have to kind of find the best trade-off by finding the best length scale that both suppresses these oscillations but also doesn't completely destroy your prediction. So that's what I, for example, saw a lot if I just applied the Tikhonov regularization to linear regression.
Yes, so, yeah. Exactly. Okay, thank you. Very interesting. Anthony?
Yeah, thanks. So this last point actually kind of goes in the direction of what I wanted to ask, because that's the connection to the Backus-Gilbert. Because so the Backus-Gilbert gives me two pieces of information, which is the resolution function and the smeared spectral function. And for the method to say that there's a limit there, this method also has to give me these two pieces of information. You kind of just said a second ago that yes, you have this parameter basically that where you saw unphysical fluctuations and this kind of thing coming in if you change the length scale. However, this is where I would argue the Backus-Gilbert method is a bit superior, because you actually can quantify this length scale through the width of the resolution function. You don't have to wiggle around and play with something. Okay, you have the, of course, you have to find the trade-off of the error. Okay, I will give that. But this kind of, I think, this kind of also goes into, it's not really a question or a comment, it kind of goes, it starts the discussion. Because in this plots here, the lattice data, I should be seeing delta peaks. I should not be seeing smooth, widened functions as this kind, because it's still data on a finite volume. And I wonder in this particular method if we know that these are delta peaks, if we are not throwing something away that is actually valuable. This is this idea of use the smearing. If you know exactly what the smearing kernel is and what the smearing function is, the resolution function that you smeared over, then you know a little bit more. And so here you could say, so here what I find very interesting, for example, is this negative dip on the left before you have the increase, because how can I get that with delta functions? How can I get that by multiplying delta for a few delta functions with some smearing function? And that would it would force me either that I have a highly oscillatory resolution function, or I have a negative peak there, just before, just to the left. And I wonder, and this is where now finally, which I will stop. I wonder what you think, how this method can then be improved into that direction, because yeah, many things said.
Yeah, so I'm pretty sure that the resolution can be quantified here in a similar fashion. I just haven't explored this direction yet, but I don't think I'm going out on a limb here if I say that it's basically very similar to the Backus-Gilbert. Regarding delta peaks, I honestly don't know. I just trust my more physically competent collaborators that this is actually the shape we expect. And so you would probably have to discuss this with them.
Oh, yeah.
But yeah.
This kind of was precisely the reason why I said it's supposed to go into the discussion, because I think this point where people say, well, this looks like the spectral function should like, has been something that has happened in the community quite often, contrary to better knowledge, which is we know that this is a finite volume spectrum, does not have any smooth limit, except for in the kind that Harvey and Max defined. So what is our goal here? Is the goal here to get the delta functions or what? Perhaps
no, this was not the goal. So I started this with the assumption that I want to get a smooth solution out of this. Yeah.
Jonivan?
Yeah, so I think, well, actually, there's two different things here. I think the point about the delta functions is certainly strictly speaking correct. So I think we probably need to keep in mind always that when we're reconstructing something from a finite volume, we are, whatever we're doing, there's some level of smearing, because we know that it's always going to be a sum of delta functions. But so we know this is non-positive. These spectral functions of non-positive operators. Essentially, the gluon is known not to have a positive definite spectral function, so we do expect negative values for the spectral function, and I guess will be a limit of a sum of positive and negative delta function peaks. I assume that if we were able to reduce it to the delta functions of the finite volume, then we'll see some negative delta functions and we'll see some positive delta functions. So that part of it probably, well, there's probably the subtleties involved through that, but that particular part isn't particularly sort of an issue, I think.
and this might go into the discussion that we will have at some other point about, for example, the generalized eigenvalue problem, and if you use different types of interpolating operators, then the positivity of the spectral decomposition is only given when you use the same operators on both sides of your bra and ket. And so that means that this the opportunity to encounter also negative weights on one's delta functions might actually be something that we have to deal with more often, as we are trying to use these more advanced methods for increasing the signal to noise, I think.
Yeah.
So should I stop sharing for discussion?
Sure. I think we can just go over into the general discussion, and maybe if there is a request by the audience, both Martha and you, of course, keep your slides at hand, please, so that we can refer